This is the first of 3 videos on what is called the integrated rate law. This one will look at the integrated rate law for zero-order reactions. Now, rate laws are nothing more than a mathematical method for determining how fast a reaction can occur under a given set of circumstances. The differential rate law, which we've already discussed, looks at the initial concentration versus rate. The integrated or integral rate law looks at concentration versus time. You're going to be looking at one reactant versus time. The data, therefore, is concentration and time. Frequently, graphing data will be helpful, and you may need to do mathematical manipulations to the data and plot the data more than once to find the answer. This method can be used to determine if a reaction is zero, first, or second order with respect to a specific reactant. We're going to define some terms. A sub t is the concentration of reactant A at some time t. A sub 0 is the concentration of the reactant at time 0 or at the beginning of the experiment. K is the rate constant, just like it was the differential rate law. T is the time elapsed in whatever unit is given. And the half-life, the T sub 1/2, is the amount of time it takes for the concentration of A to decrease by 50%. So you start with 100% and you get to 50%. That's a half-life. 50% to 25%, another half-life. 25% to 12.5%, another half-life. So on and so forth. For a zero-order reaction, the rate of reaction is independent of the concentration of reactant A. The differential rate law would be rate equals K times A to the 0 power, but anything to the 0 power is 1, so rate equals K. You plot the concentration of A versus T, and you get a straight line with a negative slope. The absolute value of the slope is the rate constant K. Another way to say that is that the magnitude of the slope and K are the same, they just have opposite signs. The y equals mx plus b equation for the line will be a sub t equals negative kt plus a sub 0. If you plot the concentration of A versus T and you do not get a straight line, the reaction is not zero order. And for a zero order reaction, the half-life is not constant. Each half-life will have a different value. So for example, let's take the decomposition of ammonia to nitrogen and hydrogen. We run the experiment and we collect this data. When you graph the data, it is obviously a straight line. This is a zero-order reaction. Just to show you how the equations come about, you start with y equals mx plus b. Since the concentration is on the y-axis, the concentration of A at time t is the y value. M, the slope, is the rate constant, but the opposite sign. So we would say that m is equal to negative k, and the x value is t, so mx becomes negative kt. And the y-intercept is the concentration of the ammonia at time 0, or A sub 0. However, this can be rearranged to A sub t minus A sub 0 equals negative kt. Same equation, just rearranged. This is how it is shown on your formula sheet. Now here it's a straight line, so the reaction is zero order. And as we'll show, the half-life is not constant. Is the graph a straight line? Can you do this without having to graph it? And the answer is yes. It's the down and dirty. If you have a straight line, the slope will be constant. So pick 2 or 3 sets of points and calculate the slope. If the slope for the 2 or 3 points is the same or exceedingly close, then your graph is a straight line. So look at 0 to 5 seconds, not going to include the units, and the slope is negative 0.125. Look from 9.6 to 18 seconds, you get the same slope. 0 to 18 seconds, the same slope. Since the slopes are consistent, this must be a straight line. The half-life isn't consistent. There are 2 ways to do this. The first is graphically, and this works no matter what. Once you have the graph, pick 2 points, with the second point being half the concentration of the first. So here I pick a concentration of 2, then I draw the line down to the x-axis to see what the time is in seconds. So now I'm going to pick 1 molar for the concentration. I draw the line down to the seconds, but I look at the distance between the two. Now I pick a third point, which will be half of the second point, in this case 0.5. Draw the line down, look at the distance. It's obvious that the 2 arrows are not the same, so therefore the half-life is not consistent. Sometimes on the data set, you can also do this. And in this data set, you can. If you look at the data, you see that at time 0, you've got 2.4 molar, and at 9.60 seconds, you have 1.2 molar. That is a half-life, and that's 9.60 seconds. You look at the rest of the data, and you see that at 14.40 seconds, you have a concentration of 0.6, which is half of 1.2. The half-life there is 4.80 seconds. The half-life is not constant, and this is consistent with zero order, but it does not prove zero order. So to review, the integrated rate law compares concentration with time. Our definitions are A sub t is the concentration time t, A sub 0 is the concentration time equals 0, t is the amount of time that has elapsed, k is the rate constant, and the half-life is how long it takes for the concentration of a reactant to decrease by 50%. For a zero-order reaction, the graph of the concentration of the reactant versus time is a straight line. The integrated rate law is in y equals mx plus b form, A sub t equals minus kt plus A sub 0. But on the formula sheet, it will look like this. The rate constant is equal in magnitude but opposite in sign to the slope. K will always be positive. And the half-life is not constant. It varies with concentration. This is consistent with a zero-order reaction, but doesn't prove that it's a zero-order reaction. And that takes care of zero-order reactions. The next video will deal with first-order reactions.